like 3-4 minutes extra. First of all, I would like to thank the organizer, especially the Vice Chancellor of this university, the Vice Chancellor, and my colleagues, and the deans, and all the people who are behind architecture. So, my sincere thank you to you all. It was very pleasure for me to come all the way and see a beautiful campus. Without sparing any more time, we'll go straight to the talk. I'll be talking on understanding the random walk with different state sizes and different. So I will lead them. This work is done in collaboration with my master's students. So the outline of the talk. So I have made the talk like a full course meal. To start with, it is an aperitif, where I will briefly introduce the idea of stochastic process, Markov process, and Markov chain. People in the back, can you hear me?
Yes.
Yes. And then antipasto, where I will introduce the random walk problem and its analysis using combinatorics. In the first course of the meal, you will hear from me the dynamics of the random walk is governed by. I'll show you the dynamics of the random walk problem is governed by diffusion. And the main course, where I will discuss the results, solution to diffusion equation, and discuss its various interesting aspects. And random walk with random step size, random walk with linearly shrinking step sizes, and what happens if the step size is geometrically shrinking. So we will cover all these things, and as a result, you will hear from me the summary, and I will talk about it. To understand what is stochastic process, the first thing we have to understand what is random variable or stochastic variable process and variable. A random or stochastic variable, which I can denote as x, is defined by a set of possible values, say x1, x2, x3, and x4, so and so forth. And that is not enough. You also need to know the corresponding probability with which x1 can appear, x2 can appear, x3, and so forth. So, what is random or stochastic variable? It is not really random. We know all the values that can come. We also know the frequency at which they come. Only thing that we don't know which will come where. That we don't know. So, for example, if you consider a dice, if you throw it, what are the values it can take? 1, 2, 3, 4, 5, and 6. And we know that these are the values, say x1, x2, x3, x4, x6. And we know the frequency with which these values can come. x1 for 1 come with probability 1 by 6. So each of them comes, so we know the probabilities are known, and these probabilities, if you sum them up, has to be equal to 1. So it's normalized. So random basically is not that random. Have I made myself clear? So yes. Once a random variable is defined, infinity of other random variables can be derived from it by simply mapping y to x. Anything that you obtain using that x variable is also a random variable. Is that clear? Fine. So by mapping sum, this can be connected by some definition. These quantities now can be a function of time as well. Now I am introducing time. Right? That means you are stacking a set of random variables along time. So you have now infinity of random variables. Clear? So if your random variable now is a function of time, system which evolve probabilistically in time, in which there exists a set of time-dependent random variable. Now I have a random variable, say 1, 2, 3, 4, 5, 6 is a dice. I have a dice which can have 7 values. I have a dice which can have 20 values. So, and I'm stacking them in a time axis. So I have infinity of random variable sitting on the time axis. Right? And that constitutes the total system now is a stochastic process. So in the stochastic process, if you take a snapshot, a cross section of time axis along there, there is a stochastic variable. And as you walk along the time axis, you are evolving, system is evolving with time. We call it stochastic. I hope things clear. I took this problem because when I heard that it's a multidisciplinary, so I thought that statistics people will like it, physics will like it, maths will like it. So it's an interdisciplinary problem actually, and one problem. So now, once a stochastic process is understood, then I can define a joint probability, meaning that what is the probability? No, something x has assumed a value x1 at time t1, x2 at time t2, and xn at time tn. So you have total drag at different time. What are the values x can assume? So this joint probability sometimes confusing. However, when you have a joint probability like that, it's a formidable task. Very difficult to solve the problem. And our difficulty is reduced. Our life has made simpler by Mr. Markov, who said that no, you don't need to know everything, the whole past history. If you want to know what will happen in immediate future, that now you only need to know what is where you are now, not where you were. That's made our life so. Meaning, you define a conditional probability which depend on Tn. So, what is the probability that object or a system is at xn at time Tn, provided system was at Tn minus 1 at xn minus 1 and T1 at x1. So, everything. But if this is depends only on that and doesn't depend on that, that process is called Markov process. So a process is called Markovian if only immediate future depends on the present, not in the past. It's simple, right? So now we can define a conditional joint distribution function for a two-variable problem in this fashion. Why is that conditional probability and this? So if we integrate it over x1, so x1 will be out of it. So probability of finding, assuming the object x value x2 at time t2 is equal to this. And I can discretize that by all that I'm saying now is to prepare the audience so that you understand what I am going to talk about. So I have not discussed my problem yet. It's only the preparation of my ground. So, and this is called Markov chain. Now, this is my problem. Random walk in one dimension, because I don't want to invite difficulty. Simplest problem of random walk is in one dimension. And also, it's not a continuum medium. I'm assuming for a simple case is where the points are a discrete. Wherever you start from walk, your walk, I call it its origin. x equal to 0. And then I label them 1, 2, 3, 4, 5, and minus 1, minus 1. And worker, I give a fair, honest coin to the worker. Each time he makes a step, he tosses the coin. If it is head, he makes one step to the right or to the left. And if it is tail, he makes a okay? So you have two options. You can go either to the right or left, depending whether it is head or tail. And assuming head and tail comes with equal probability, meaning probability half and half. Right? So, right. No. This problem was in 1905 and as miracle year বলা হয় কেন in 1905 Einstein published 4 papers which had revolutionized modern physics. One of the papers for which he won the Nobel Prize was on photoelectric. The second paper he published was on Brownian motion, which is now the random walk, the one I mentioned. The third paper was on theory of special relativity. And fourth one was on relativity, but with E and square. This fourth paper is revolutionary. That's why it is called miracle year. Not only that, in the same year, Carl Pearson is the famous scientist philosopher at the time. In fact, Einstein got motivation by reading his book called Grammar of Science. The relativity idea was conceived by Einstein by reading that book written by Carl Pearson. Carl Pearson in the same year, 1905, published one article with one question on it, few lines. Question is below: if I work randomly, what is the probability that I will be at position M? He asked scientists all over the world to give him an answer. He could find answer for few steps, but he wanted to know this general formula. What is the probability after making n number of steps he is at position M? And that has been what updates its nature. And scientists all over the world they tried. And since then, it is regarded as a random walk problem. It is still known as the most interesting problem, most ubiquitous problem. It has the most application. Although Einstein got Nobel Prize for photoelectric effect, this one is no less important than any of the other three problems. However, since those are more elegant, glamorous, people only now know, but this still, if you open any journal in physics, you find still what's going on. Now, if you are making step 1, what is the probability you will be finding at position 0? With step 1, there is no chance you will be at position 0. So probability is 0. Making one step to be found at 1, probability half. Minus 1, probability half. And if you add the 2, you get probability 1. Similarly, with step 2, you can be at position 0 with probability. How many ways? You can go the right and come back. One way. You can go to the left and come back. You are still at 0. The probability. So how many ways you can make 2 steps? There are 4 ways. And out of 4 ways, only 2 ways you can return to the position you started at position 0. So this is a simple problem. But Kamrul Hassan wanted to know answer to this question. So, to reach at position M, you need to give n plus number of steps to the right and n minus number of steps to the left, subject to the constraint n plus and n minus equal to n, total number of steps n. And then, if you do a little bit of calculation, you can find what is n plus and n minus equal to plus. If you add, if you subtract, you can find and that is the answer. This many ways you can make to the left, this many ways you can make to the right, and total number of ways you can make steps and number of steps 2 to the power n. So, how many distinct paths? How many distinct paths? By making n number of steps, you can be at position n, this many distinct paths. Total number of paths is 2 to the power n. So if you take the ratio of the two, you get the probability. And that was the answer to the question he made in the nature. Now, if you take a log on both sides and apply the Stirling approximation and do some little bit of algebra, I don't want to go in details, you'll be lost on that. So finally, we can show it's a continuum solution. Now, I want to show to you that random walk is governed by the dynamics of the random walk is governed by diffusion. To do that, I invite the Markov chain that I shown you out here. So this is the transition probability that you are at position m delta. Delta is the minimum size between two steps. In between, that is size, that is constant. So you are at position m at time s tau, at time t, and you want to know the probability to be at position n delta immediate after that time, 1 time unit after. And this is connected by this relation. How can I apply this condition to describe my problem random walk? And to do that, I have to choose the transition probability. This equal to, meaning I am at position m. Then I cannot go m equal to m plus 5. Because in one step, I can go either m plus 1 or I can go to the m minus 1. Right? Therefore, and each of these events can take place with probability half. So this half and half is due to that each of them can occur with probability half, and m can be m plus 1 because I am at position m. If I go to the right, it is m plus 1. If I go to the left, it is m minus 1. So n value has a constraint. It cannot just assume anybody it likes. It has to be, so that has to be is ensured by the delta function. So if I substitute this into there, then I get that. And then from both sides, I subtract m and g. And this is the equation, it's called master equation. Master equation because it's a loss and gain term. If you are already at n, my Pn is showing that evolutionary time is a counter where the walker is. And the counter counts if the walker is at position n. So if you are already at n position, you can never stay in n next time you need. So it's lost term. But if you are at position n plus 1, there is a chance you can be at position n with probability half. If you are at position n minus 1, there is a chance that you can be at n with probability half. So these two are gain terms in class. Anyway, this will be plus 48. I corrected it from something like that. So again, after doing some, I don't know to go all PT. So if you do this some algebra, finally you can see If I assume that n delta equal to x, I'm going to continue on limit. S tau equal to t time, then I find that PXT, the probability of finding Mr. Walker at position x at time t evolve with time following a diffusion t. That's good. So it's a connection between first temporal part, first derivative of time with respect to time, and second derivative with this space. That was the question that Einstein in 2005, so in 1905, he published. It means that the dynamics of the random walk is governed by diffusion equation. In other words, it says that we can simulate. You see, the importance of this, I can find and to show that random walk is governed by diffusion equation, meaning all the phenomena in physical world that makes diffusion, I can now simulate in the computer, because computer doesn't know language by itself. I have to give the argument. So what I do to describe diffusion, I say, "Oh, mister, you just walk like a random walk, transfer walk." So random walk problem is connection I just discussed that helped us. This is the only reason why we can simulate diffusion in computer. One significant achievement. Now, I want to solve the diffusion equation in such a way so that you can gain deep insight into the problem. What do I do? You see, P on the left hand side, and its coefficient is del by del T. P on the right side is capital D times del square by del x square. And these two quantities must bear the same dimension, otherwise there's no way you can justify, you can put the equal sign. So, meaning this is dimension and that dimension must be the same. Simple dimensional analysis immediately lead you to the conclusion that T inverse or x square must bear the dimension of T. Meaning, I can now define a dimensionless quantity. X by square root of dt must be a dimensionless. At this point, I find it worthwhile to define what is dimensionless quantity. Most people, many people, from my experience, I saw that in my class, even students, the masters, they don't know what is dimensionless quantity. A quantity is called dimensionless if the numerical value of that quantity remain invariant. If you measure it in centimeter, kilometer, nanometer, doesn't matter. So if the numerical value of a quantity remain invariant and independent of the choice of a unit of measurement, that quantity is called dimensionless. Say for example, length is dimensional, it's not dimensionless. So numerical value at a meter, if you measure it in centimeter, it will be 100. So it is a dimensional. But pi is the length of the circumference and diameter ratio. Now, doesn't matter how big the circle is or how small the circle is, the circumference divided by diameter is always a pi. And doesn't matter whether you measure it, this length, you measure it kilometer, centimeter, millimeter, regardless, numerical value will be the same. So, a quantity is called dimensionless quantity if the numerical value of the quantity remain invariant upon transition from one unit of measurement to another unit of measurement. Have I made myself clear? Yes. Student with the pen. And I'm going to use that idea. That's why I'm emphasizing over and over again that it is very important for you to understand what is dimensionless quantity. It's so powerful definition. You will see. So, what I'm saying that this relation led me to define a dimensionless quantity as x by square root of dt. So if x depends on dt, that means t also can be expressed in terms of only t and t. And therefore, dt to the power theta, I don't know what value theta, I will soon find out that this also has to be dimensionless quantity. And this quantity exponent theta will be fixed by normalization condition, because sum of the probability equal to 1, so that will fix the value of theta. So, and immediately we find that, as I said, the dimensionless quantity is independent, okay, of the unit of measurement, so immediately lead to this structure. So now this is compiled through that my problem is now x and t are joined together and become one variable. I had 3 variables, x, t and t. Now the problem is only one variable, x by square root of t. And the solution of pxt, the structure is given there. All I need to know is the value of theta and solution to phi. So, and this must be equal to 1. If I plug this here and demand both, so 1 means dimensionless quantity. After plugging it here, if I demand that Mr. Hey, you have to be dimensionless as well, it will immediately give me the value theta to the minus 1. After that, I plug this solution into my diffusion equation. After a couple of steps, I get this. And this can be written as like that. Identity. And immediately I can integrate this. I get a constant. Using the boundary condition, I find the solution of that. So if I know the phi, I already know the theta, I have the solution. That's the final. Remember, if you see that solution, if I go back, this is the solution using the combinatorics. And this is the solution I found directly by solving the equation. Students in the back, can you hear me? Clear? Can you follow? Yes, sir. Okay, am I going to class? No, sir. Now, problem is solved. Now, what are the beauty of this solution? First and foremost, if I replace x by -1, minus x, the solution is invariant. So, number one, interestingly, is the pxt equal to minus pxt. That means there is a mirror symmetry. The solution, left hand side and right hand side, and if I fold it, they will be invariant. So, number one. And then, if x is changed, unit of measurement of x is changed by a factor of lambda by 2, lambda to the power b by 2, and lambda to the power b, t is changed by this factor, then the solution is like that. It's called scale invariant. The solution is scale invariant. Then also, generalized homogeneous function is another property. And pxt exhibit dynamic scaling, which I will soon discuss. But remember the name, word. It is called dynamic scaling. Very important aspect. And then, by using the recursion relation, if I am at, after n number of steps, if I am at x position, then, say for example, I am at x, n minus step I am here. I want to know where am I now. I can be plus delta or minus delta. And I can iterate this. By iterating, I can get the mean value is x. That is, on the average, actually, I'm always at 0 position. So this is not very interesting. But however, the variance name And then I find that this relation is not what Mr. Einstein did. That was his solution in 1905. And T, he made the connection with the viscosity, with the Avogadro's number. That's why it is so important. This solution has another importance. You know, Boltzmann and few other scientists, they were trying to get a new idea that the system is made of atoms. And they were resisted. They had few, all the big scholars like Wilhelm Ostwald, Ernst Mach, these are the leading philosophers at that time. They made Boltzmann's life so miserable. And he committed suicide for that in 1906. Unfortunately, if he had waited a few more years after Einstein's paper, those people who didn't like the idea of Boltzmann, they were silent by the Einstein's paper. From then on, idea of atom, people understood that yes, it is a fact. So Boltzmann had to die for the idea that he was trying to promulgate, that atomistic idea. So in fact, so this is a very powerful case. The kinetic theory of gases, all this in there. Now, I can, in fact, before just coming here, I have read a paper that Newton's, during the time of Newton, there was one open problem, could not be solved. Only last year, people solved the problem. The distance between two planets among the three star or planet could be solved by using the drunkard walk, random walk. So random walk is still relevant. Now, I can find the mean-square displacement by using the diffusion equation. I can diffusion equation if I multiply on x and integrate, I find mean is 0. By multiplying x squared, I integrate by integrating, I find that. So diffusion equation itself shows that root mean square displacement is g to the power half. Now, how can I simulate the problem in the problem and verify all the results that I have shown now? What shall I do? So, in the simulation, we ask many workers, say capital M number of workers, at the same time, I have given each of them a fair coin. And I told them, for example, if I give you a fair coin, each of you, and I give you the instruction that toss. If it comes head, you make one step to the right. If it comes tail, to the left. And you make n number of steps. All of you. And I ask, where are you finally, after giving n number of steps? So I find what fraction of the total worker is at position 0, is at position 1, 2, 3, 4, all these things. And then I plot, and then I regard as P. I plot as a function of x. You see, at x equals 0, the peak is 0, and it is plus x and minus x. If you replace, you see that there is a mirror symmetry. Right? So Px equal to P minus x, number 1. Another thing is that interesting that when you have time 1000, peak is maximum. Meaning you are asked to make 1000 steps. Instead, if you are asked to make 6000 steps, you are there. That means peak value decreases. with number of steps. And each step is considered to be a time. Say 1 second, 1 minute, 1 day, doesn't matter. 1 time unit. So that means as time increases, the peak decreases. This is number 1. We want to know at what fashion, how this peak value decreases with time. To know that, I take the peak value as a function of time, and then I plot log of P max, log of time, I get a beautiful shape. Meaning, P decreases with n number of steps following a power law with exponent half. Meaning, and n is nothing but time. That means P decreases with t to the power minus half. My solution here is also say that P decreases following the. So my numerical solution is perfect. Agree with my analytical solution perfectly. It matches. Beautiful. Okay. So, and next, I thought, since P divided by square root of dt, meaning P divided by t to the power minus half, if I bring it up, then if I plot this, I see all the P collapse into one point because this is the dimensionless quantity. As I say, when numerical value of the dimensionless quantity doesn't change, so it collapses. And then now I measure the full width at half maximum. So the full width at the half maximum. And then I plot them as a function of t in the log scale. I find again a beautiful straight line with exponent half. Meaning, root mean square displacement, full width at half maxima goes with time. That means if you are for longer time, there is a probability you will find in a longer distance. And that distance increases with time. Right? So now, if I x is scaled by divided by t to the power half, it should be again dimensionless quantity. So x is scaled by t to the power minus half, t is scaled by t to the power minus half, and then if I plot, I see that all the distinct curve beautifully collapse into one curve because this is a dimensionless quantity, that is a dimensionless quantity, and hence the numerical value remains invariant regardless how many steps you have given, always the same. Data collapse. And data collapse also perfectly confirm the solution that I obtained analytically and by numerical solution are perfect. Now, what is the meaning of this data collapse? I will give you some example. A very simple example, even I hope that all of you will understand. Say, for instance, I have 3 right triangles. I have 3 right triangles of different size. And assuming that all this has 3 angles, these angles are same. I measure the area as a function of height. So I will change the B and I measure the area. So I plot the area as a function of B. So this one, for each of them, I get 3 different baselines because we know that AS equal to half moving equal to half. So our A, this one is A. So higher the A, the slope will be higher. So the bigger A has this one. The smallest triangle has this one. Now, if I divide PE by the hypotenuse B by C, become B by C the dimensionless quantity. If area is divided by C square, that is also dimensionless quantity. So this same data, if the area is divided by C square and the length is divided by C, all these 3 are collapses. Meaning all three triangles are similar. So data collapse means similar. You see, architect, before building a large building or ship or airplane, they first work on a tabletop model. If the tabletop model, all the experiment you do on the tabletop model, if you cannot connect to the real system, the modeling is useless. So modeling is useful only if the experimental data can be connected to the real system, and that connection can be established by this idea of data collapse. Meaning, this truth has to be similar. The numerical value may differ between the two, but corresponding dimensionless quantity between the model system and the real system must be same. If they are same, we call they are similar. So, the geometric similarity can be easily extended to the physical similarity, which I have shown that random or diffusion problem, they all data collapse, meaning if I work for no matter how long I work, they are similar. In the sense, consider that Big Bang, universe big, and then evolving. You take a snapshot, you take another snapshot, you take another snapshot. So each of them may represent one triangle, as I mentioned before. And corresponding data, dimensional data, will have distinct curve, but corresponding dimensionless quantity will coincide, data collapse. Meaning what? This when the universe is expanding, preserving one thing in a fashion, they are similar. So the system is evolving with time. So what is dynamic scaling? So a system is probabilistically evolving in time. Anytime you take a snapshot, all these snapshots are similar in the same sense as two triangles are similar. Clear? Next, I want to address the question, what if, so far I have said that each state are equal in size. You may ask, so what if my state sizes are random? Will it be a different solution? In fact, in real systems, you see the state size is clearly not same. So, if you resolve for different step size, solution is different, then diffusion equation you can throw it to the bin. It has no use. But fortunately, even if I choose random step size, for example, if you have a line here, and I randomly chop it. The more I chop, the intervals will become equal and more equal. Infinite number of terms, meaning that I will have 1 by n, 2 by n, 3 by n, these are the numbers. So if the step size, each of them are this size, if I choose from them randomly, these are or if I choose them, I order them in a descending order, the longer I go, I get tired, smaller the step size is, still I get the same solution. And still they show the data class. So solution is robust. Robust doesn't depend on the step sizes. Have I made my message clear to you all? It's so robust. If it were not, it would be useless. It is useful because of this. Now the question comes, what if step sizes are geometrically shrinking? Meaning, now, only recently I have done this work and published in a journal of chaos, solution and fractal with my students. So this is my work contribution. So far I have discussed, I prepared you to create an aspect. What are the things that we have done? And now, only for the last 3 years, for the first time, we found a departure from the known result. Subject to the condition, the state sizes decreases geometrically. In what fashion? So, I choose nth step to be of size this to the power n. Meaning, the first step will be n equal to 1, the biggest step. Second step is smaller, but smaller with a multiplied square. Third step, multiply to the power cube. Okay. Fourth step to the power 4. In that section, I do the calculation. I can even find the mean square displacement analytically. I show for the first time root mean square displacement for the first time and new result instead of t to the power half we found t to the power 1/4. Not only that, the p decreases also as a t to the power 1/4 or minus 1/4. And that's why now t to the power 1/4 and t to the power minus 1/4, if I plot instead of t to the power half and minus half, beautifully collapse into one. Suggesting that my solution, analytical solution, perfectly matches. And this is our first result. That is what happened. So, to summarize, we have extensively studied the theory of actually like by mistake the one that basically does what was the different night. Somebody got so I can finish it. But I would be glad to answer any question that you have. Yes, well, what we do, let's measure the macroscopic. সবাই মিলে যে ফাইনাল আউটকামটা হচ্ছে we are interested in that. Temperature we measure. What is that? It's a macroscopic variable. সবার সাথে collision হয়ে বা মুভমেন্টের কারণে যে kinetic energy হয়, they measure of that kinetic energy. Similarly, random walk problem, individual walk can go this way and that way. It's a random, but despite it is random, finally macroscopically it follows some rule. Macroscopic. So this is one factor, but any of them. Electron complicated is the quantum mechanism coming. There is one small problem. So when you go there, that microscopic level, then you have to invite another problem for yourself. So it's different. If not any more questions, then you have questions. The question is, what if the problem was not Markovian? Meaning, if you have memory, that's it. But thanks God, most of the phenomena in nature, even all the phenomena that you have ever studied, they don't have it. So, immediate past is all you need to know. Thanks God, we don't need to know what happened in the past and past. It's আমরা বাংলাদেশের আমরা খালি past, but atoms and molecules, they only to decide what will happen. Why they have them. There are problems, yes, but simple matters, simple problems, simple solutions.